Good afternoon. My name is Jamal Abdalla. I'm professor of civil engineering at the American University of Sharjah. With me, Professor Rami Hawileh and engineer Khalid Mohamed, who graduated from the American University of Sharjah, and myself and Rami supervised his master thesis, and this is part of his work. The title of my presentation today is Use of bore-epoxy anchorage system with CFRP sheets for shear strengthening of reinforced concrete beams. The outline of my presentation as shown here is to start with the introduction, then problem statement and objectives, background and literature review, scope of the work done, experimental program, experimental results and discussions, and then conclusion and references. Introduction. Well, we all know that building deteriorates over time, and especially reinforced concrete buildings. And the reinforced concrete buildings, the members of it has different modes of failure. For beams, for example, shear failure is the most undesirable types of failure. It's a sudden and it's a brittle failure, and we should avoid it by all costs. This figure shows two types of shear failure on beams. We said that material properties get deteriorated over time, okay? And this could be due to many reasons. Corrosion of steel, for example, makes steel lose some of its strength. Carbonation of concrete. Also, buildings need to be strengthened due to the fact that there is some changes in the function of the building. That means the dead load or live load may have been increased due to the new function. Design codes evolve continuously over time, and sometimes new requirements in the code emerge, and therefore the building has to satisfy these new codes. Sometimes the design itself was poor from the beginning. Some natural things may happen to the building, seismic forces that happened in the building, wind load or something like that cause some kind of weakening of some members, and therefore those members need to be strengthened. So these are all reasons that why strengthening is needed for building. Aims and method of strengthening. Well, the aim of strengthening is to increase the building or the member strength, stiffness, ductility, durability, and so forth. That's the main thing. And also sometimes you have only two options: either to strengthen the building and use it, or demolish the building. And demolition usually is costly because you need to rebuild again. So therefore, strengthening could be the economical choice. Okay. What are the different methods for strengthening? Well, there are many different methods, but externally bonded reinforcement is one of the most widely used methods for strengthening structural members. Example of strengthening, the top one is the flexural strengthening of beams using externally bonded carbon fiber reinforced polymers, and the one at the bottom is strengthening in shear, which is like a U-wrap of the stem of the beam to allow it to resist more shear. Well, what are the materials used for externally bonded reinforcement? Well, there are many materials used. Steel was the first one, especially started in the 60s, before that. And then galvanized steel mesh, which is recent high strength steel that's been developed in recent years. And then aluminum is a newly emerging externally bonded reinforcement, which has also high strength aluminum alloys. Of course, fiber reinforced polymer is the most widely used one, and there are different types of fiber reinforced polymers. There is a carbon fiber, glass fiber, basalt, and aramid fiber, and there are other types of fiber that in the market. Use of fiber started not recently, but in the 80s, both. Well, of course, the CFRP or the carbon fiber reinforced polymer used a lot because of many advantages. It has a high strength, very high tensile strength, of course. It has a lightweight with density of 4 to 6 times lighter than steel, high fatigue resistance. The installation of it is easy. and it resists corrosion. And also can be used both for flexural strengthening or for shear strengthening or for confinement of columns. So there are many different ways of using the carbon fiber reinforcement, and it has many statement and objectives. Well, one of the problems that we face with external bonded reinforcement is the debonding that happens between the say, carbon fiber reinforced polymer and the concrete surface. Okay, so that's debonding usually result in having the material not being used to its fullest strength, and therefore that will result in less strengthening than what we expect. So in order to avoid premature debonding, engineers use anchors. And anchors are used for the CFRP laminates in order to increase their resistance, whether shear or flexure. Okay, so basically the objective of this study is to explore the use of bore-epoxy anchors for two-sided CFRP sheets in order to delay or prevent debonding and therefore increase the shear capacity of the reinforced concrete beam. So here it's talking about bore-epoxy anchors for shear. Okay, and also we will study also the mode of failures of the tested beams with or without background and literature. Well, FRP is, strengthening and design philosophy is becoming a very well-studied area. Many researchers have published analytical models and some shear design equations and so forth to predict the shear capacity of externally bonded reinforcement. The ACI 440, this is specifications from the American Concrete Institutes that they deal with fiber reinforced polymers for beams, columns, and so forth, shear, flexure, and so forth. And it has everything from selection, design, installation, and others. And it has been used by quite a while. We mentioned that one of the ways of delaying or preventing debonding or premature debonding is use of anchors. Over the years, there are many different anchors that have been used for anchoring shear, externally bonded shear reinforcement. U-wrapping was one of the one that you just saw in a picture a few slides ago. Full wrapping of anchors, FRP spike anchors, mechanical anchors, grooving methods or grooving anchors, or boring anchors as well as and there are many other types of anchors. Each of them has advantage and disadvantage and a specific use. Okay, I'll go over two of them, which are basically one of them is both of them are epoxy based anchors. The first one is a groove epoxy anchor, which is developed by researchers. One of them is David. In 2012, he presented members that had been strengthened with externally bonded reinforcement that was put on grooves, and he used small specimens, which the dimensions shown there, and he showed that the capacity of the strength of the member has increased, and it reached maybe up to 23%, and the failure modes changed from debonding to just flexural failure, as mentioned. Another type of epoxy-based anchors, which you bore epoxy anchors, which is basically this is the main topic of this presentation. Iftikhar in 2015 presented some prisms, small element prisms, in which he proof of concept of how the bore epoxy can increase the shear, can increase the capacity. Here is our flexural capacity, basically that was used. And there are small specimens, and they conclude that the flexural capacity of the section is increased by up to 35%. Okay, what did we do in this work? So the scope of the work that's covered in this presentation and the matrix or this matrix of the specimen that we handled are follows. We cast 5 members, both are beam members. We'll see the details of each of the specimen in a minute. So we have the first one is being kept as a control. Then we have another one, which is externally bonded reinforcement. And the S here is all 4 sheets. We are using carbon fiber reinforced polymer sheets, not plates. So this S is 4 sheets. Okay, then we have another element, SBM and SBM and SBL. So we have all these three elements. They have been externally strengthened with externally bonded reinforcement, but we have anchors or bore epoxy anchorage that was being used. Here is diameter of the bore anchors, and here are the other dimension that you see, and here is the figure showing some. Okay, experimental program involve beams were designed as shear deficient beams. Stirrups are provided only on one side, as you can see in the left-hand side. The right-hand side, there is no stirrups provided. Okay, and therefore the right-hand side will be strengthened by externally bonded reinforcement with or without bore epoxy anchorage, as we will see. Okay, these are material properties of the used. Okay, the experimental program, we said preparation of the specimen, drilling the here. Then we have the testing procedure. We have the specimen mounted in infrared. You can see it over there. Results that we produced. Well, the control beam, as shown here, is failed in around 113 kilonewton, and that's very close to the one that predicted by the ACR. Here is a control beam, and you can see the diagonal shear failure that happens. The load deflection curve for the control beam is shown here. Maximum deflection is 5. Okay, the second element, which is the externally bonded reinforcement with sheet, is fail around. And the failure, you can see here the debonding of the externally bonded reinforcement. There is a debonding, so that means it's not utilized to its full strength. So the next specimen, we used bore epoxy anchors to anchor these external bonding. Okay, this is the load deflection for that specimen. This one is we have a bore epoxy anchorage with narrow diameter, and you can see the failure here. The debonding maybe in one or two of the reinforcement. The rest of them, they did not debond. This one with medium size boring, and you can see that the failure is not by debonding of the external reinforcement, but rather by delamination, because some of the concrete has been taken out with the reinforcement, and the last one very similar. The debonding has been prevented. So the absence of the debonding here, or delay of the debonding, caused more shear resistance by the member. And here are the three load deflection relationship for the three member that has bore epoxy. Summary of the results here, and you can see the last two columns showing you the increase in load capacity and the increase in deflection due to the bore epoxy anchors, and it's obviously there's here very much the same result. In conclusion, the control beam failed in shear as expected with diagonal tension cracks, and that's the load it takes. The second control member, the shear capacity increased by around 41%, and the deflection is by around 51%. This is the one that is strengthened with external bonded reinforcement without anchors. And then the remaining three with the anchors, they showed even more shear load capacity and even more deflection, as shown here in the figure, in the previous figures. Well, debonding of the CFRP plates happened in the one without anchors, while the one with anchors, there is no debonding took place, and therefore that means they are more ductile, and therefore this increased the shear capacity, as well as make the shear becomes more ductile rather than brittle failure by having more deflection shown. And I think with my conclusion, here are the references, and I'll be ready to answer all questions. Thank you again.